Standard Model of Particle Physics. The Standard Model is the theoretical framework that describes all known elementary particles and three of the four fundamental forces governing their interactions: electromagnetism, the weak nuclear force, and the strong nuclear force, while excluding gravity too. Elementary particles. Quark 6. Flavors: up, down, charm, strange, top, bottom combine to form protons, neutrons, and other hadrons. Leptons 6. Flavors: electron, muon, tau, plus their corresponding neutrinos. Electrons and heavier muons, taus, carry electric charge. Neutrinos are electrically neutral bosons, force carriers. Photon, electromagnetism. W and Z bosons, weak force, gluons, strong force. Higgs boson, responsible for giving mass to particles via the Higgs mechanism. Fundamental forces: electromagnetic force. Infinite range, carried by photons, governs interactions between charged particles. Weak nuclear force, very short range, carried by W and Z bosons.
Responsible for radioactive decay and nuclear fusion in stars. Strong nuclear force, very short range, carried by gluons, binds quarks together inside protons and neutrons. Gravity not incorporated in the Standard Model. Its hypothetical carrier, graviton, remains undiscovered. Theoretical framework gauge symmetry based on the internal symmetry group, SU, 3 cross SU, 2 cross U, 1 SU, 3 governs the strong interaction, quantum chromodynamics, SU, 2 cross U, 1 unifies the electromagnetic and weak interactions into the electroweak theory. Higgs mechanism introduces a scalar Higgs field permeating all space. Spontaneous symmetry, breaking of the electroweak force, gives mass to W and Z bosons into fermions via interactions with the Higgs field. Quantum field theory. Particles are excitations of underlying fields. Interactions arise from exchanging force carrier bosons between matter fields. Historical milestones: 1928. Dirac equation predicts antimatter. 1954. Yang-Mills gauge theory formulates non-abelian interactions, 1967 to 1968. Electroweak unification by Glashow, Weinberg, and Salam. 1973. Discovery of asymptotic freedom in quantum chromodynamics by Gross, Wilczek, and Politzer, 2012. Experimental confirmation of the Higgs boson at CERN's Large Hadron Collider. Experimental validation. The Standard Model has been tested through countless experiments and precisely predicted phenomena such as weak neutral currents and W/Z boson properties, existence of the top quark, 1995, and tau neutrino, 2000, mass and decay channels of the Higgs boson, 2012. Limitations and open questions: gravity remains outside its scope. A quantum theory of gravity is needed. Dark matter and dark energy, approximately 95% of the universe, have no Standard Model candidates. Neutrino masses and oscillations require extensions beyond the minimal model. Matter-antimatter asymmetry in the universe remains unexplained. Beyond the Standard Model. Ongoing efforts aim to address these gaps by exploring grand unified theories, GUTS, that merge strong and electroweak forces. Supersymmetry predicting partner particles for every Standard Model field. Extra-dimensional frameworks and string theory as potential quantum gravity candidates. Direct searches for dark matter particles and precision neutrino experiments. Moving forward, experiments at the LHC Run 3, next-generation neutrino observatories, and underground dark matter detectors will probe the Standard Model's boundaries and point the way toward a deeper, more unified description of nature.